Another speaker that is Leson. Leson is a professor in Georgia Tech, and actually he works in two different topics. One is kernels, but since you already heard quite a bit about kernels, he's going to talk about the other topic that he has been interested about in recent years, that is social and information networks, and in particular more like dynamic processes that take place over them. And has been incredibly productive on this topic, and actually is one of my collaborators. So without further ado.
First, I'd like to thank the organizers for such a great event. Yeah, and Cardiff is such a nice place. I enjoy very much. Okay, so now today I'm going to talk about social network analysis. Of course, I'm not just going to talk about the static social network. I'm going to talk about the dynamics of a social network. So nowadays, actually, it doesn't matter what research you do. Yeah, you will invariably encounter network. So it doesn't matter whether you work on social network problems, or work on computational biology, or even work on electrical engineering. You have power grid network, you have transportation network. So you invariably encounter networks. So in the past 10 years or so, people have, or 15 years, people have been working a lot on social networks and large-scale networks. But most of this research has been mostly focused on just the static aspects of these networks. For instance, you might have already heard about things like the scale-free networks, right? And 6 degrees of separation, and then small network, things like this, right? You have seen probably some of these plot of the degree distribution of the network, or the average distance of the social network, things like this, right? And but there's more to it. The social network itself is not just static. It is the backbone for information propagation. It's the backbone for spreading information, people communicating with each other. Actually, nowadays, when you look at social network, and you invariably collect lots of data. So it is not just a static network. On top of this static network, you're going to see lots of activities generated by the user. For instance, in Twitter, in 1 minute, you are going to have 98,000 tweets. So this is already a number a few years back. Okay. So all of the network structure remained pretty much constant in a short period of time. The amount of activity generated in this static network is huge, and the network itself is going to also evolve over time. So all these data generated in the social network are mostly some type of data I would like to call event data. I'm going to essentially give you a little bit more concrete example. What does it mean by event data later on? So it's some kind of discrete events happening continuous time. For instance, you tweet about something. You tweet at a particular time point, right? Happen at a particular discrete time point. And then, but these events happen in continuous time. We have continuous time. Okay. So here is a hypothetical example. You have this discrete event happening in continuous time. For instance, there are two people interacting in social network. One is David, one is Sophie. They're connected to each other via Facebook or Twitter. At some point, 1 p.m., David just tweeted about something. There's a cool picture somewhere. Okay. And then Sophie follow up very quickly. 1 minute later, say it's indeed very cool picture. Okay. And then David posts another piece of message in 18 minutes later, and it's just posting a very funny joke. And then Sophie follow up these tweets very quickly and say yes. And then David have another tweet at 1:30 p.m. and then asking whether you want to go for dinner tonight. And then Sophie answered very quickly, okay. So here, every time David posted something, Sophie follow up very quickly, okay. So there's sort of the time information reveals a very strong influence from David to Sophie, right? So obviously, if you ignore the temporal information, you might not be able to deduce such a strong influence from David to Sophie, right? So that's why temporal information is so critical, when you try to analyze these kind of social network data. So you can actually have exactly the same tweets, but you just change the temporal information a little bit. You will have exactly opposite meaning. For instance, again, David posted one day, David posted exactly the same message. There's a cool picture. But after 14 minutes, and then Sophie reluctantly say, indeed, it's a cool picture, okay? And then David quickly followed with another message at 1:15 p.m. Okay? And then somehow Sophie is lukewarm, and then only after quite a while, Sophie replied, exactly the same content. And David followed with a message immediately. Right? And then after 20 minutes of long consideration, in the end, Sophie replied, Reluctantly, okay. So only these two settings, and the content are exactly the same, but because the temporal duration of these interactions, these events, um, completely change the meaning of these interaction contexts. That's why it is so important to look into temporal information, right? In this social network, look at dynamic process, modeling this temporal information in social network. Then here comes the question: how do you actually model this type of temporal dynamics? Yeah, we need a language, we need a framework to model this information. Yeah, and once we have such a model, we might be use it for other downstream tasks, maybe influence maximization, things like this. Okay, wire marketing, things like this. Okay, so let me just abstract a little bit of this type of data, and then very often you will see a picture like this in my talk. Here is a particular user in the social network, and I'm going to draw a timeline for this user, and then you will see some spikes here. Okay, each one of these spikes is going to denote one event. So it has a precise temporal information, timing information in it, and it might also have content information. For instance, in this particular case, it's just the contents of the tweet. Okay, so you might have already learned about the time series models, right? Just for finance, you maybe also for capital process. The most familiar one is time series models. So one thing you might think about to model this type of data is I'm going to just divide this temporal axis into different epochs and then use traditional time series model for it. Okay. So what you're going to do is I'm going to partition this time axis into epoch 1, 2, 3, right? And then I'm going to somehow aggregate information within each one of these epochs and use the traditional time series analysis approach to do it. But very quickly you will find that you are going to run into a problem. The first problem is how do you actually choose this epoch, right? Whether you should choose it as 1 minute, 1 hour, or 1 day, things like this. Yeah. Actually, if you look at different pair of people, the temporal sort of resolution or the speed of interaction between different people is very different. It's very hard to choose a unified length for the epochs, okay? And then use time series model. This is the first problem. The second problem is once you fix some epoch, invariable in your data in this type of event data, you'll find that sometimes in some epoch you will have more than one event. And sometimes in some of these epochs you have no events at all. So then you wonder what do you do with it. For instance, in the case where you have more than one event, in one epoch you'll have to aggregate it. You have to do something, okay? You don't know what is the best to do. And when you have no interaction, are you going to assign 0 or some other information? That's another design choice you need to make, which is not easy. So from sort of a graphical model point of view, you can also think about this time series-based approach as some kind of treating this temporal information as some kind of conditioning variable. It's a little bit like the covariates in the Gaussian process if you have attended class. So you condition on this time tree as some kind of index. What's running on top of it is probably some kind of counts. And then once you use such a model, the difficulty for later inference is, suppose I ask you to predict what's going to be the time for the next event. Then for this type of model, which conditional time is going to be very difficult. Okay, so essentially, if you consider all these drawbacks of traditional time series model, you'll find that it is actually not a good idea to discretize the time into epochs and then just use traditional time series model. You need a new language to model this type of data. Okay, so that's exactly the framework I'm going to teach you today. Okay. So this is sort of the example in social network, but you find this type of temporal dynamic data or event data in many different type of applications. So it doesn't matter whether it's working on social network, whether you work on industry or academia, you invariably encounter this. So even you, for instance, actually the spread of information in social network is very similar to the scenario of spread of disease among people. Okay, you can use very similar type of model. Or you have some kind of computer virus spreading in these computer network. You can also model this type of discrete events happening in continuous time. So nowadays, if you look at some of these healthcare data, it's also going to be event data. Essentially, people go to clinics or hospitals, right? There's a precise timestamp you recall where this patient is going to the hospital, and also other symptoms, things like this, right? And then one of these patients can go to the hospital at any point in time. Yeah. It just depends on the progression of the disease. You have collected lots of data from different patients. So you can use this type of time process model I'm going to talk about today to model this kind of information. The The same thing you want to build a smart city. You can record the space and time of each one of these taxi pickup and drop off, right? And you want to forecast when is going to be the next taxi drop off and pickup, when is going to be the distribution of a taxi in the city at different point in time. So you get all these type of event data. The same thing if you care about sustainability problem for conserving wildlife, okay? So, but today I'm going to just focus, or not today, or in these two lectures I'm going to focus just on 3 applications. But once you see how this point process model is being used in these 3 applications, you should be able to generalize it and use it for many different type of applications, okay? So the first scenario, or the first application I'm going to use is going to be this so-called, it's like a viral marketing, yeah.
Sorry to interrupt. In the previous setting, we are only on non-distributed setting, like centralized. When we store the data, one computer has the data.
Yeah, so in this lecture, I'm going to mostly talk about, you have already collected all this data in the centralized data center, for instance, Twitter, right? Or Google, for instance, Uber, they collect all this data in-house. But you can think about the more advanced algorithm, when you actually have these agents moving around the city, they somehow need to collaborate with each other in a distributed fashion. That's going to be some additional interesting fashion. So I've not touched upon that, but you can definitely build upon our research and do more in this direction. Right? So the first scenario I'm going to talk about is these information diffusion or idea spread or idea adaptation kind of scenario. It can also be applied almost directly to the disease spread among people and viral marketing setting. So in this particular setting, you again have this hypothetical social network, and the direction of the arrow in this social network is pointing towards the flow of information. Yeah. So essentially, if I have an edge pointing from D to S, David to S, that means S follows David. The information is going to flow from David to S. So in this particular setting, when you have idea adoption, for instance, David has a nice idea, right? And he's going to propagate to his neighbors, followers. So at some point in time, David talk about his idea at 1 p.m. And then Sophie may just adopt the idea, may like the idea, right? Or like the product at 1:18 p.m. And once Sophie like it, and she is going to propagate the same kind of sentiment, likeness, okay, or the idea to his downstream neighbors. And this downstream neighbor is going to affect it at a different point in time, okay? So this is a very simple scenario. When you have a single piece of information which is propagated across this social network, we're going to use this type of a unified framework to model this type of scenario. Okay. So the second scenario I'm going to focus on later on in the lecture is going to be something called coevolution between information diffusion and the network evolution. So it's very similar to the scenario where you will see in Twitter. So it actually builds upon this previous idea adoption type model. So in this particular case, and again, you have this social network, suppose a Twitter network. They will tweet about something at a particular point in time, right? And each one is message they will generate is going to have his identity attached to it. And then the follower, Sophie, is going to retweet it, right? At another time, 10 minutes later, and then the information is going to propagate to downstream Christine, okay? Christine also like it. Every time that this information gets propagated in Twitter, so actually the identity of the original information is recorded, right? So in Twitter you see something like this, add somebody, right? So it's telling you the original source of the information. And then this Bob may also respond to it at different point in time, 118, and then Jacob is going to, in the end, respond. Indeed, brilliant, okay? So in this particular case, information is propagated from David to Jacob. And then the source of this original information is always acknowledged in the message. So at some point, David finds the information originated from David is really useful, right? Really useful. What he's going to do is he's going to direct link to David. Okay, he's going to create a direct link to David instead of follow through these intermediate passive messages. Okay, so he finds that the message from David is very useful. That's why he created a direct link to David. So the propagation of information helps people discover useful source of information and help people connect to the information source. So the network is going to change because of the spread of information. Okay, that's what happened in the Twitter. So you can actually model the simultaneously this information diffusion and creation of the edges, new edges in the information in some sense, you can use this type of techniques for generating an evolution model of the network. Okay. So once you have this new link, the information propagation is going to be completely changed. So for instance, the next time David tweeted about something at 2 p.m., then Jacob is no longer following through all these intermediate messages. He's going to directly respond to David's message very quickly. After 3 minutes, he agrees with David. So this has already changed the information propagation path, right? So this is the second scenario we will talk about. It turns out you can use exactly the same methodology to model this type of scenario. So the third scenario happened a lot in all these online shopping kind of websites. For instance, it doesn't matter you go to Amazon or you listen to music in online stores like last I said, Spotify, right, or Pandora. So you are essentially collecting lots of user behavior. In this particular case, you have, for instance, 4 users, and then they're going to purchase 4 different items. So actually, you're not just recording whether this guy buys the product or not. So you're actually recording where you find temporal information about when this particular person buys a particular product. Essentially, if you look at a pair of user and product, okay, so you're recording a timeline. Right? This timeline is just recording when this guy is buying a particular product. Yeah, supposedly you're able to model this type of people buying products, temporal dynamics. What you want to do is you want to predict, yeah, what is the next item this person want to buy and when he needs it. Okay, so then you can recommend the item to this person in the right time, right? So you want to do something like time-sensitive recommendation. So if you don't model this temporal dynamics, so you won't be able to recommend the right time. So, so the unified framework I'm going to introduce today is focused mostly on temporal information. Okay, modeling. Okay, this is the 3D scenario. So how are we going to basically structure the material? I'm going to largely divide the material into 4 chunks. The first chunk I'm going to introduce you this important quantity called intensity function. It's some concept from point processes, okay? And then it's very useful for modeling various type of discrete event happening in continuous time in social network and many other applications. And once we finish this basic building block, okay? So I'm going to use them to model these 3 scenarios I just mentioned: idea adoption, network coevolution, and collaborative dynamics. Of course, all this model invariably has some parameter in it. So what we want to do is to estimate the parameter from the data. So in the third chunk of this tutorial, I'm going to talk about how we actually estimate the parameter from real-world data, real-world user activity data collected from the web. Okay. So it turns out that you need to solve some kind of convex optimization problem, and many things you learn in this tutorial, early tutorial, can be used for tackling this problem, especially for extremely large-scale problems. And once you learn this model, you want to do some kind of inference, prediction task, for instance, predicting when this user is going to buy the next item, okay? How many people this particular tweet is going to reach in 1 month, things like this. You want to do inference, answering query related to time. So then I'm going to talk about 2 applications, where the first one is so-called time-sensitive representation I mentioned. The second one is how do you do inference estimation and maximization, okay? So today I think I will pretty much cover just the first 2 chunks, and then tomorrow I will cover the next 2 chunks. So for the intensity, okay, so how do we actually motivate this intensity? Now I'm just taking one of these users in social network, right? So I have already attached to this user a timeline. I'm going to record all these events or the time when this guy posted a message, okay? So this is going to be the timelines of the data. So we need to sort of provide some kind of mathematical framework to it. So to do this, typically you will sort of represent this history of David as something called the counting process. So it is just some integer, non-integer assigned to this user, which is going to change over time. So it just counts how many events that has been generated by David at a particular time t. Okay, very simple. Every time you see a new event, you're going to increase it by 1. That's the counting process representation, right? And the question is, once you have this history of David, so how do you model the time point for the next event? How do you model this temporal dynamics? How will this history determine the location or the time location of the next event? So that's the thing you want to model, right? So we all know about random variables. Supposedly you have some kind of density function or conditional density function given the history of this next time interval. So one thing you can do is you can just sample from this density function, right? And then that will give you a sort of particular instantiation of the next event. So, I will explain to you that density function is actually not a nice quantity to use when you try to model this temporal dynamic. Intensity function is a better quantity. So before I go into that, I just want to introduce some related concept. The first one is the density itself means that if you look at a particular small time window, right, t and delta t, the density is going to give you the small probability, the probability you see an event in this small window, right? And a related concept is something called survival probability. It's the probability that the event has not happened before time t. So it is just taking this density function and integrate the right-hand side. Okay? So this area under this curve. So it's going to be the survival probability. Okay? And once you have this density function, of course, you can write out, yeah, if we want to model this sequence of user activity probabilistically, once we have this density, conditional density, we, in principle, can write out the likelihood of particular instantiation of the sequence of time, right? So what you do is that you're going to compute the conditional density of each one is a time point, right? And then in the last time interval between t and t, does nothing happen. Yeah, suppose you only have an observation window of t, and then you see event t1, t2, t3, and t here for event, and no event happening here. So you can describe this entire sequence of events by just product together the likelihood of individual events. So each one is event, you have one term in the likelihood, and then for the last interval, you have some survival function because nothing happens here. Okay. So I don't know whether this lecture will have any graphical model or related contents. Typically, when you try to parameterize density, yeah, so you in machine learning you use something called exponential family model. Okay. So one thing you will do is you will essentially compute some sufficient statistics of your observation time in this case, and then you're going to have some parameter which is linear in its sufficient statistic, and then you say the probability of seeing the particular, or the density or likelihood of seeing the particular time is going to be proportional exp of this parameter in the product with the sufficient statistics, and then you normalize it by some kind of constant. That's just some kind of exponential family model, right? So we typically choose such a parameterization for density like this, okay? So each one term is going to have one density. In the end, you have this survival function. It's just 1 minus integral from 0 to t, right? And you can write out the likelihood. But what you will find is when you try to estimate parameter using this formulation, you get something called the non-convex problem. So in this particular case, we try to maximize likelihood. It's not a concave problem. So convex optimization is intimately linked to machine learning. If you don't have a convex optimization, but typically it's much harder to estimate parameter. Although you can still do it. It's much harder, and it's much harder to give guarantee. So you will actually get something non-convex, not so nice, when you use likelihood. So later on, I will show you that there's some other benefits of using something called intensity function rather than density. You have lots of intuitive meaning of intensity function when you try to use it for modeling the actual applications. So this is one drawback of using density function. So we need another quantity that is easier, okay? So these other quantities called intensity function. This is one key slice you should remember, okay, if you don't remember other things. What is intensity function? It's built upon this density function and survival function. So if you have density function and survival function, the definition of intensity function is just the ratio between the density function and survival function. It's some kind of conditional probability distribution type of concept. If you look at this small time interval, the intensity function means that given that the event hasn't happened between 0 and t, the conditional probability is going to happen in this small time window. It's a conditional probability type concept. Okay? So So it's also linked, obviously, to this density by product together of this intensity and the survival function, you will get density, right? And then actually there's another more complicated relationship. We can actually also get survival function based on intensity function alone. So the nice thing about intensity function is you don't need it to be normalized. When you talk about density, it's always normalized, right? When you integrate from 0 to t, density is going to normalize. But for conditional intensity, you don't need to do that. So you just need this function to be non-negative. Then you can call it an intensity function. Essentially, you can design lots of meaningful intensity functions depending on your application. We are going to see lots of interesting examples for it. So if I put in a diagram, and it's actually very easy to link together this conditional intensity function with your familiar quantities such as density and cumulative distribution function, the survival function. Suppose you have your density function f over there, so you can get the cumulative distribution by just integrate from 0 to t, right? And then you can go from cumulative distribution function to density by just taking derivative. So you can go from this cumulative distribution function, survival function, by just 1 minus f is survival, and the 1 minus survival function is cumulative distribution function. And the ratio between these density function and survival function is going to be the intensity function. And from the intensity function, we'll go back to survival function and then density function by these two formulas. So what we are going to focus today is to parameterize this guy. Okay? So all the definition is the ratio between the density and the survival function. But once we focus on this quantity, we're going to just parameterize directly this quantity. Rather than going through first defining density and then compute this ratio, we're going to directly define this density, okay? This conditional intensity, okay? So as long as it's non-negative, that's fine. Okay, any question about this? Yeah.
So do you have any way to directly write from S to H or from small f to H?
S to H.
Some links are not direct.
Yeah, so you need two. You need two things. So it's so you can write it. So if you have density, right? You need to go through first compute this, and then you take the ratio, you will get this, right? So in some sense, if you have one of these quantity, you can get other quantities, yeah? So they are related, but somehow when you try to model these temporal events, and it's much more convenient to use this. You will get Combs optimization problem, you will get lots of meaningful stuff out of this conditional intensity function, right? So the first thing is we mentioned that the drawback of parameterizing the density function. If you parameterize conditional intensity function, then it's much easier. Actually, you can write out the likelihood. Since with the conditional intensity, you can get back to density. You can actually write out the likelihood of this sequence of events as well. So in this case, if you write it out, just substituting all this density with conditional intensity, right? So you get an expression like this. Each one of these events is going to have one intensity term associated to it. And in the end, again, you have this interval, which has no events. It's going to have a survival function. And if you parameterize, for instance, this intensity function as some kind of linear model, it doesn't need to be normalized. That's why we don't need this exp something or divided by z, okay? As long as it's non-negative, that's fine. We just parameterize some kind of linear model here, and then there, okay? So once you take log of it, yeah, log of this likelihood of the entire sequence of events, you're actually getting some kind of concave or convex optimization problem because we are maximizing it. That's why it's concave in this parameter W. So that means even if you have millions of data points, you can think about efficient optimization way to learn the parameter and with the guarantee as well. Okay. So here I use some notation that the phi is again some kind of sufficient statistical data you design from your data, and then the psi there, the psi star there is going to correspond to the integral of these sufficient statistics over time. Okay. So it's just change your notation a bit. We will use this likelihood later when we talk about learning the parameters for these time processes. Okay? So the first benefit you get using intensity function is you will get Combs optimization problem. And then later on we use this property for estimating the parameter from actual data. So but now I'm going to focus on some examples for this intensity function. Some very simple but meaningful examples of the intensity function which can use as building blocks for more complicated models. So the first example is something that you're very familiar with, I believe. It's just called Poisson processes. Okay, so it is used for modeling the arrival of bus in some bus stop, arriving of telephone call and telephone call center, things like this. So what Poisson process is doing is it's assuming that somehow the occurrence of the events, is spread evenly across time. Okay? Yeah. So and then the time interval, the interval between two events is going to follow exponential distribution. So if you actually parameterize using this intensity function, it's super simple. It's just the intensity is going to be a constant. It doesn't depend on the history. Okay, it doesn't depend on a particular time point. It's always a constant. Okay, so in this particular case, right? So that will give you a process which is essentially, the event is going to happen uniformly over time. Okay? So it has been used in electrical engineering and queuing theory, but we can actually use this as a special case for modeling social activities. Yeah. So suppose you believe that somehow some people log into the website is something like uniform across time, then you can use Poisson process. Yeah. And actually, another question related to these processes is once I have designed a particular condition intensity function, and then how do I actually sample data from it? Right? How do I actually generate or simulate data from such a model? So actually, for Poisson process, it's super easy to simulate from based on this parameter. So what you do is you first determine a time interval 0 to t, right? So actually, this is t. Okay. And then what you do is you generate a uniform sample, yeah. And then you take a log transformation and divide it by this mu. Okay. So you are just going to sample from the uniform and do a transformation, yeah. And that's going to be the time you get is going to be the sample from these processes. Okay. So it's very simple, yeah. But this simple generative process is used later for generating more complicated data from other processes. Okay. So this is clear, but very easy, right? MATLAB, you just generate a uniform sample, and then you do this transformation, yeah? And then take a log, and then divide it by the intensity function. So the meaning of this intensity here is, suppose mu is high, right? That means that you actually see more events in a unit amount of time, right? So if u is large, and then you get t very small, that means the next event comes very far, very quickly, right? The time gap between two events is going to be small. You're going to see the next event very quickly, okay? If mu is small, the intensity is low, that means that you rarely see any events, right? If mu is small, this ratio is going to be super big. The next time point on the event you're going to see is going to be far away in the future, okay? So it models this essentially the how likely you are going to see an event. But this event is going to occur more or less uniform across time. So this is the one basic building block. You just have intensity equal to a constant. So you also have something called an inhomogeneous Poisson process. So in this particular case, again, you just design your intensity function to be some other function, which depends on the time, but doesn't depend on the history. It doesn't matter whether you have T1, T2, or T3 already. So it's not going to change the forms of the intensity function. You're always going to have your intensity function, according to a particular fixed function of time. Okay? So it doesn't take into account history. If you have lots of events in the past, it's not going to change the intensity in the future. Right? The process is going to always sample from a fixed intensity. Okay? So this is a generalization of Poisson process. When you don't have uniform across time, but you have fluctuation of events across time. For instance, when the intensity here is high, you might be more likely to see more events. When the intensity is low, you don't see events. Okay? So this is the homogeneous Poisson process. You can also, essentially, the one way you can make this inhomogeneous Poisson process is you just design some kind of function, yeah, across time. For instance, if you want to design an inhomogeneous Poisson process, which with intensity like this, so what you can do is you can actually use some idea from kernel matter. Okay? So what you do is you take your time interval, window from 0 to t, partition into a lot of small grid, and put on top of each one of these location some kind of kernel function. Okay? And then you do a weighted combination of this kernel function, you get this intensity function. Okay? And then once you have this intensity function, you just use it as the intensity of the inhomogeneous Poisson process. Right? So this is the homogeneous Poisson process. And then, of course, you can design many other interesting intensity functions. For instance, one of these intensity functions is called time-related process. Here, you constrain the number of events that can possibly generate from this process. So, for instance, you can constrain the number of events to be just one event. As in each instantiation of this process, if there's one event already generated, then the process dies out. Okay, so there will be no other event generated from the process. You have to start it again to generate it. So the way you parameterize this intensity function in this particular setting is you're going to look at this count, right? This counting process, counting the number of events that has already occurred for the particular person. So you see whether it's 0 or 1. Okay, if it's 0, then you are going to generate event according to this intensity function. If it's already 1, the difference is going to be 0. It's going to zero out the intensity. You are not going to have any event anymore. Okay? It's just a combination of inhomogeneous Poisson process and some quantity which depends on the history. Right? You can imagine that you can actually turn this process to something more advanced by changing this to 2, 3. Yeah? You can allow for 2 or 3 events to happen before you zero out the intensity. Right? It's just a combination of homogeneous Poisson process, and some turn depends on the history. Right? So in this particular case, the intensity itself is actually depending on how many events you already had in the past. So it's different from the homogeneous Poisson process. Right? It doesn't depend on the history at all. In this case, it depends on the history. Right? So, yeah.
Could you just provide a simple example of how that can be useful?
So, for instance, this is useful later when we try to talk about the idea adoption or the spread of disease. In that case, a particular piece of idea, you can only adopt it once. Okay. Once you adopt it, you like it. You won't like it for the second time. Okay. You cannot pass it for the second time. Okay. Or it's some kind of food, right? You capture it once, and then you're not going to capture the same food again. Right? So this is a simple example. So this is a time-related process, very useful for those cases. And then this one is also interesting. So it's slightly more complicated. So it's called the Hawkes process or self-excitation process. So it's going to model the history in such a way. So essentially, you're going to design your intensity function as some kind of base intensity constant. Okay, base intensity like a Poisson process. Yeah, constant. So you're going to take into account the history. You're going to look at all these events which has already happened in the past. In this particular case, it's going to be T1, T2, and T3. Okay. So each event happened in the past is going to contribute one term to this intensity function. So essentially, you're going to put something like kernel function, yeah, exp, on top of one of each one of these events. Okay. So if your time point of interest is farther away from this previous event, the influence of the history is going to decay, essentially. So what I have done here is this exp function is something looks like this. Right? So I'm going to put one of these exp function on top of each one of these events in the history. I'm going to sum them together. Okay? So in the end, if you have lots of events happening in a small region, yeah, then it's going to, when you sum them together, it's going to boost the intensity. Okay? That's why it's something like excitation. If you have lots of events happening in the past, your intensity is going to be high. It's just like you like a particular maybe TV series, right? You watch it today, and 2 minutes later, 3 minutes later, you're going to watch the same type of movie again or type of program again. Okay? Yeah. If you go to a particular place recently, for many times, it's likely you're going to go there again. Or if a particular people tweet about it, okay, you retweet very often about that particular people, then it's likely that you're going to retweet again. Okay, it's just capturing this self-excitation effect. Okay. So when you sum them together, this intensity is going to look like that. It's going to depend on history. Sometimes you also see people write these self-excitation Hawkes process in such a manner. So it's going to write it as some kind of convolution between this kernel function and the counting processes. Okay, so this is more mathematical. So,
do you still get a feasible model if you say that you include a market property, so where only the last event is sort of exciting, so that now all the events in the history contribute, right?
yeah, that's right. So it's a long memory kind of process. Yeah, everything in the past in theory is contributing to the intensity of the future. It's just the influence of past events is going to decay over time. Right? You can actually pick other kernel function here. Here you pick a particular exponential kernel function. You can think about other kernel function. So you can generate. Yeah.
So is it still feasible if you say only the last event is sort of exciting?
No, yeah. So it's really the recent past history. If you have lots of recent past history, then when you sum them together, it's very, very large. If you only have one event, it's not large enough, right? It has effects, but it's a cumulative effect of the entire history. Right? Okay. So this alpha is controlling that how strong is the inference from past events. So it's sort of chaining off between the inference from past and these Poisson intensity function. Right? Okay. So when you have this more complicated intensity function, including this inhomogeneous Poisson process, terminated process, or Hawkes process, you might also want to sample these data processes from the data from the model, right? So you can actually use something called rejection sampling or feeding process to sample from it. As long as you're able to sample from these homogeneous Poisson process. The way you do it is, suppose we already have a historical event T1, T2, T3, and then the forms of this intensity is going to be like this. You want to sample a particular time point or event in the future, right? How are you going to do it? So what you're going to do is you're going to compute something called the H0 here. Yeah, you're going to take all this history and plug into the formula, yeah, and evaluate H star T3. Okay? So essentially, you're going to compute accordingly like this, and then you're going to construct hypothetically a homogeneous Poisson process with intensity H0. Okay? So you're going to sample from a Poisson process with intensity H0. You get a time point, and then you're going to go through this second stage of rejection. If this sample is going to be kept, okay, with the probability proportional to the ratio between the actual intensity function, H star T, and this H0. Okay, it's just like a rejection sampling. So you sample from homogeneous Poisson process and look at the actual intensity. Yeah? If the actual intensity is high, you're going to be more likely to accept the sample. Right? So you can use the same approach for all the other more complicated processes. And later on, when we talk about generating sample from information diffusion or the coevolution network, we are always using this type of approach. Okay? So although there's also some communication issue there, you can potentially design more efficient algorithm to do it. Okay? But the basic idea is here. So you just construct this homogeneous Poisson process as a proposal distribution. You sample, you reject. Okay? Very simple. Okay, now you have these three building blocks, essentially Poisson process, inhomogeneous Poisson process, and terminated point process, or also Hawkes process. Okay, so then you can actually combine these things together to generate more complicated processes. And then later on, we'll see how we actually combine them with the social network to generate very interesting real-world type of processes. So the first thing I want to talk about is this composition of these things together is like the superposition of processes. For instance, if you have a particular user David, right? And then I want to superimpose a few processes together. Yeah? And then, for instance, the way I superimpose these processes is going to be, I'm going to sample some event from some Poisson process with a constant intensity mu, right? I'm going to also sample from another process in homogeneous Poisson with intensity like this. Yeah, another process with intensity like this, another process with intensity like this. I'm going to get in a sample from each one of these processes. Okay? So after I generate a sample from each one of these processes using this rejection sampling or feeding procedure I just described, and then I'm going to do this operation called the minimum. I'm going to look at the minimum of these time points and just keep the sample of this minimum time point as I call it a new sample. Okay? So this procedure of first sampling a time point for each one of these processes and take the minimum, it's called a superposition of these processes. So if you do this time point t you generate is going to follow a process essentially like that. Okay? The intensity of this two-stage procedure, first sample from each one is 10, and then take the minimum. It's going to correspond to an intensity like this. You just sum together these intensity functions. Sum together mu, and each one is the exp. Okay? So every time that actually when you design some kind of intensity function which has additive form. Okay? It's going to be sum of bunch of turns. So the process, the actual kind of assumption you're making for this process is there are several independent processes. They're going to sample according to their own intensity function, and after that, you just take the minimum. Okay? So this is a very useful way to try to model the spread of information or the adoption idea. Suppose you have a few, you are following a few people, right? And then both of your ancestors in this graph or the people you're following already have the idea. So you're going to change your opinion or adopt the idea because of a particular person. It's like this. Okay, each one of your ancestors, the people you're following, is going to generate a process. Yeah, you're going to adopt the idea when a particular piece of information arrives to you the first. Okay, so this is going to be something like this. So you can superimpose these processes. For instance, you can also talk about the inference of one person to another person. So this is called a mutually exciting processes. So you just have two people, Davy, right? Davy has his own processes, dynamic processes. It has this intensity function which corresponds to the Hawkes process, is something like this. And then Sophie also has intensity function, which is something like this. In general events, it has an intensity function like this. And now I want the Sophie to inference the sort of events from Sophie to inference Davy. So I can actually just superimpose these two, okay? I just add together. So I have the original self-excitation process for Davy, and now I'm going to add some additional turns due to the historical events from Sophie. Okay? Yeah.
How do you treat the case when both David and Sophie have a job at the same time?
Yeah, so this is difficult mathematically, but in practice it's not a problem. So it's not exactly the same time. You can always perturb it, but it's a bit. Okay? Right. Yeah. Or in that particular case, you can also go to more advanced case called Mark prime process. Okay. So we are not going to talk about that in too much detail, right? So this particular case, when you add together the intensity of Davy and Sophie, and trying to use this superimposed intensity to describe the behavior of Davy, is essentially going through this superposition process I just described earlier. So Davy is going to tweet about something, either because of his own history, right? Because he has already tweeted about a particular topic for many times, he's going to likely to tweet. Or it can be because of inference from Sophie, because Sophie has such a strong inference in Davy. So exactly which cases is the driving force for creating this particular event depends on which process is going to sample an event at a small values for the time. Right? So it's just like this case. So this is the process for the Davy. This is for Sophie. And this is for another person. This is for another person. Right? So the actual event generated in Davy is going to be determined by the event which generated the sample earliest. Okay. So the meaning of this is superposition of the processes. Okay? So you can also combine Hawkes process with other processes. Right? For instance, you can have Davy, which has this terminating prime process. You only allow Davy to generate one event. He can only purchase that product for once. So you just have this history-dependent term and some inhomogeneous Poisson process term. And then now you can make Sophie to inference Davy. Sophie may talk about this product very good every day. Okay? And then he is going to inference Davy. Okay? So you're going to superimpose two terms together. Right? So you're going to add this inhomogeneous Poisson process with this Hawkes process and history from Sophie. And then you will still have this history dependent. Once David purchased a particular product, it's not going to purchase again, for instance. Okay? Right? The intensity is going to look like this. You just sum together the intensity. That's what you get. Right? Okay? So now we have this essential building block. And then a very simple way of adding them together or a superposition of this process. We can use it for more and more complicated cases. Okay, the first model I'm going to talk about is idea adoption or the spread of virus, okay, viral marketing. So you'll find that using this quite closed framework, it becomes very natural. Yeah? So this is the sort of continuous time information diffusion model. You have such a network. And then each person in the network can potentially be the information source. Okay? And you're going to describe each one is present by now counting process as well, right? So for instance, you're going to describe the event happening in David by the counting process. Suppose David is the information source. So the count is always going to be 1, okay? So at the beginning, okay? If David is the source. And then suppose I want to describe the process of Jacob adopting the particular idea, right? So for instance, I can also describe it by counting process, right? So whether Jacob is going to adopt the product depends on whether Christine involved, which is the parent of Jacob in the social network, has already adopted the product or not. In order to describe whether Christine and Bob has already adopted the product or not, so essentially you need to assign a counting process for Christine and Bob as well. Right? So now you have this counting process recording the history of this user. What is left for describing the dynamics is actually designing this intensity function. Right? How do you actually design this intensity function? You're going to design something closely related to this terminating point process. Okay, you're going to use this terminating point process to design it. So what this intensity is going to look like? So it's going to, Jacob is going to have, the intensity is going to have 2 terms. It's going to be superposition of the inference from the parent Bob and also the parent Christine, okay? This A is just like a adjacent matrix of the network, yeah? Because Bob and Christine is the parent, so this Jacob is 1. Otherwise, the entry in the adjacent matrix is 0, right? So you just aggregate, superimpose the inference from the parents. And then you're going to, again, also check whether Jacob has already adopted the idea or not, right? If he has already adopted the idea, you're going to zero out intensity. And then you're also going to look at whether Bob has already adopted the idea or not, for instance, right? So just see whether the count is 1 or not, or 0. So you just design this intensity in a way that incorporating real-world scenario. You just look at your parents, Christine and Bob, and see whether they have already adopted the idea or not. If they have adopted the idea, it's going to have inference on Jacob. You just add together this inference of the parents, right? Exactly who is the actual parent which transfer the idea to Jacob, depending on this competing process, right? For both essentially, both this term is going to generate an event, and this term is going to generate an event. The actual event is going to be the one which has a smaller value. Okay, so you just put together a few terminated point processes. Then you get this idea adoption type of model, right? Any question about this? Okay. So earlier we talked about how you actually sample this event from the intensity function, right? So you can also sample. Once you have the intensity function, you can also sample from this intensity function. You can generate something called cascade based on this model. So of course, now I'm just writing out the intensity for Jacob. Similarly, you can also design an intensity for Bob. Right? Then the intensity of Bob is going to be superposition of 2 times. In this case, 1 time is going to be just coming from the parent Sophie. Okay. So you can do this for each one of these nodes in this network. So once you have done, you will be able to essentially sample these time points from this the process. Suppose the David is going to be the source node. Initially has the idea at time point t0. Then you're going to sample according to this intensity for the actual event time for Sophie, for Bob, and Jacob, and Christine, things like this, right? Suppose I am just limiting myself to 30 minutes of my simulation horizon. So in that particular 30-minute simulation horizon, maybe only these 3 nodes are fully infected, okay, or adopting that particular idea. So that particular sample, yeah. So it's a sequence of time points. It's going to be called a cascade. So the next time you can sample again, start this infection again and sample again, you get a different sequence of time points. If you look at the 30-minute kind of time window, only 1 node is going to be infected. So you can sample again, right, according to this point process. You will get another essential cascade. Okay. So when people talk about this cascade data, it's just something like it's essentially you have a bunch of users, and then one of these users is going to be the information source. And then, for instance, the earliest the user with the event, which has smallest time, then it's going to be the source. Then it's going to trigger a cascade essentially recording this cascade as a collection of time points. Okay? So people call this cascade, but essentially it's just a sequence type. And you can have a different source node, and you generate a different cascade. You will have another essentially source node. You generate a different cascade. Okay? That's just a cascade. So you can essentially sample from these process the cascades. Okay? So this is putting it in this point process framework. Once you understand the intensity, and then using those building blocks for composing and make complicated processes, it's really easy to build this type of information diffusion model. Yeah, you just put together this time in a point process, and you get an information diffusion model. Right? It's actually the coolest information model at the moment. Yeah. It's simple, and then in this convex optimization, it's easy to sample. It can be used to compute efficiently. The inference of particular node can be efficiently carried out, the inference maximization, things like this. It's just that simple, right? Okay. So this is the information diffusion model. So you can also design intensity to generate more complicated process. The second model I want to talk about is this coevolution model. Right? So in this particular case, you have two processes. One is the information diffusion process, right? Very similar to this previous model, but we are going to use a slightly more complicated process for it, the host process. Like Twitter, you can tweet many times, right? And we are going to use that kind of model. I'm also going to model the evolution network. Right? Okay. So I have two processes here. I want to sort of simultaneously model. So in this, let me just remind you of this setting. In this particular case, it's more like Twitter, right? David tweeted about something, and Sophie is going to retweet. So she's going to acknowledge the source of the information. So similarly, when this tweet propagates to the downstream users, this user is always going to acknowledge the origin of the tweet. Okay? At some point, Jacob finds that the information is useful. He's going to create a direct link to the original source. Okay? So this is a link creation. That one is information diffusion. Once you have created a new link, it's going to change the way information diffuse. David is going to tweet about something again. Now the information is going to propagate directly to Jacob instead of going through these intermediate nodes. Okay? So and then how do we model this? So first thing is in terms of representing all these events. So in this particular case, since each one is tweets is acknowledging the original source of that tweet. So we are going to recall each one of these events in this social network as a triplet. Okay? So it's going to So we're going to record it as some kind of triplets. And then the first element in this triplet is going to be just the person who actually retweeted it. And then the second element is going to be the information source. So Jacob is retweeting the tweets from David, okay? I'm going to record the information source as well. And then also the temporal information. So mostly in the talk, I'm going to involve this other information like text. I'm only going to talk about the text in the very end. How do you actually incorporate the text information? Yeah. So you are going to record this event as triplets: the destination node, who retweeted, and the original tweets and the time. Okay. And I'm also going to basically represent each one event edge creation or link creation as some kind of triplets. It's going to be the destination node, source node, and then time when this edge is going to create it. Okay. So it just has a little bit more index here, right? So essentially you're recording the temporal information of it. Okay? And of course, there may be tweets originally from other users, not just from David. It might be tweets originally from Bob, right? So these original tweets, the tweet and Bob are originally from Bob. At this particular time, I'm going to record like that. So Jacob, you can retweet Bob instead of David as well, right? That's why this particular event has the source node, which is Bob here. Okay. So of course, Jacob also can generate original tweets. It's going to be JJ 5 p.m., right? And then Jacob also can create links to other users. For instance, Sophie is going to be J, source is going to be Sophie, and this particular time points. Okay. So you're just going to record your event like this. So now you have more things to keep track of. You need more counting process to denote these events. So essentially, if you think about these retweets, just forget about the link creation for a moment. Just look at the retweets. So essentially, you will create a one point process for each one is sources. Okay, so it's for this particular user Jacob, it's going to have one point process for each one of these original source for David, Bob as well. Okay, we're just going to record how many times Jacob has retrieved a particular information source. Okay? For link creation, similarly, you can also create this collection of point process for Jacob. For instance, whether Jacob has linked to himself, is always linking to himself, okay, supposedly. And when Jacob is linking to David, okay, when Jacob is linking to Sophie, okay, because in this particular case, link creation can only happen once, okay, that's why you only see one event. Sort of, we also give you a little bit hints. We're going to actually assign slightly different intensity for link creation and retweeting events. Okay, we're going to essentially use Hawk's process, mutual excitation process for the tweets and retweets, but for using terminating point process for the link creation. Okay. You can actually also take into account the link deletion process as well, but I'm not going to talk about it here. So essentially, for now, we're just going to, once you have these mathematical representation for these events, now what's left for describing this temporal dynamic is to design this intensity function. Right? First thing, for David, which is going, so suppose we have to design the intensity for David generating original tweets. Okay, so it's just going to be a Poisson process. David is going to tweet just randomly. Okay, uniform plus time. Okay, so he's going to sometimes like it, just tweet it. Okay, it's just a Poisson process. And so now how do we describe the Jacob's retweets? The tweets originated from David. Okay? So we're going to design a Hawk's process for it and the superposition of Hawk's process. Essentially, it's going to look like this. Okay? It's going to depend on whether these, before Jacob actually linked to David, we're going to, the retweets of Jacob to David is going to depend on whether his parent, Christine and Bob, has retweeted David or not. Otherwise, he's not going to see it. Right? So that's why you also need the counting process of Christine retweet David, and then Bob retweet David in the picture in order to describe the sort of the retweets of Jacob to the David. Okay, so once you have these several quantities, the intensity function you design for Jacob to retweet David is going to be something like this. It's going to be superposition again of the two sort of inference, the inference from two parents. The first term is again just a Hawk's process, looking at the events from the parent Bob, right? And then this is a Jason's matrix again. If it's connected, it's 1, otherwise it's 0. And then this is the term that comes from another parent, Christine. Okay? So this BD really captures the strength of inference. Yeah? And this kernel sort of function here is capturing temporal decays of inference. Okay? If B is large, then every time that Bob and Christine retweets to David, it's very likely that it's going to trigger a particular event in Jacob retweeting the tweets originated from David as well. Okay, so this beta has this type of meaning. So when you try to model this retweeting behavior to according to the source from the tweets from original user, then you can use this type of we call it targeted retweet because you actually acknowledge the particular information source. Okay? So this is for retweeting behavior. How about the link creation process, right? So link creation process again, depends on how Jacob retweeting likes David, right? So Jacob is going to connect to David if he finds that he's actually retweeting lots of tweets originating from David. He finds that David is really useful to information sources, and then he decided to link to it, right? So he actually, whether Jacob is going to create a link to David or not, depends on how frequent or how intensive Jacob is retweeting the tweets from David. Okay, you're going to design an intensity function like this. Okay, so I'm going to design intensity like this. So this edge between Jacob and David is going to be AJT. Yeah, it's some kind of counting process of calling time. So it's either 0, 1. And then you're going to first look at whether there's already a link between Jacob and David or not. Right? So if he already has a link, it's going to zero out everything. Yeah. And then you're going to have two terms. One term is essentially again the self-excitation process. Okay, you just look at how frequent Jacob has repeated data. If Jacob repeated data very frequently, right, then Jacob may find that data is really a useful information source. It's more likely that Jacob will connect to data. So this part of intensity is essentially captured that, and this alpha is sort of deciding how strong this self-excitation is there. Okay, and then you have another term which is Poisson process here. Yeah, essentially just captures the sort of with some random probability. Yeah, Jacob will connect the data. Jacob is just going to explore this network randomly, and somehow with small probability you can connect to a particular person. Okay, so you can capture all this. So essentially, overall, it's something like a big terminating point process, right? And then the checking condition depends on whether the edge is already there or not. And then the actual driving force of creating the edge is the intensity, this Hawkes process, right? And also this Poisson process. Okay, you can compose all these things together and then build all these kind of complicated models. So now essentially you have two parts. The first part is you have actually three parts. The first thing is this diffusion network. Right? It's just a adjacency matrix, which has at each particular time point, this matrix is going to be recording either 0 or 1. Right? It's going to change over time because we will have a new edge being created. And then once you have this particular adjacency matrix, so it's going to support this information diffusion process. Right? When we describe these targeted retreats, we actually need to use this adjacency matrix. So David is also going to receive information if he has directly connected with someone. Right? And then once you have this information diffusion process, it's actually driving the creation of new link as well. In some sense, it's changing this adjacency matrix, and you have this closed loop system. Okay, so you just put together these targeted retreats, and then this link creation process together. You get this joint process of information diffusion and coevolution. Right? So it's just again using this building block, terminating point process, the Hawkes process, the Poisson process, but you can have infinite number of combinations and many interesting processes generated from this exercise. Okay. Right? Any question about this? Yeah.
Again, sorry. If we want to really use that, is it going to be able to scale? Like for instance, for Twitter, we have 500 million users.
Yeah.
The matrix already is too big to be stored.
So it's a sparse matrix. Yeah. So you don't actually store it as a full matrix. You just record the adjacent non-zero entries.
Yeah, but about the link creation process, it's here to especially be able to create new links whenever we want. So we have to consider every possible link, or is this link creation process also sparse?
So link creation process you can make it dense. Right? You can make it dense. You can consider, for instance, this one. Right? This one is you can potentially randomly connect to every edge. Right? Yeah. But before you create that link, you don't need to keep track of it. Before you create it, you don't need to keep track of it. And this term only keep track of the tweets you have retweeted it. Okay? If you have never returned originated from someone, you don't need to keep track of it. Only when you start retweeting the particular tweets originated from someone, you keep track of that intensity. Before you actually do it, you never keep track of it. That's why you don't need to worry about the scalability of it. Okay? Okay? Yeah. This is essentially the information diffusion link creation process. Yeah. You can also actually add link deletion process into it. You can also add things like the additional new nodes into the process. Okay? You can have many things on top of it. Okay? So once you have such a process, you can sample, right? Using the rejection sampling, we just described earlier. And it's just a slightly more complicated intensity function. And you can generate a network like this, and then the blinking of the nodes is essentially corresponding to the retweeting behavior. Okay, so if you retweet something, you're going to have a blink, and then at some point it's going to create some edge, connecting to a particular information source. So in this particular case, we have fixed number of nodes. That's why you see the network is growing denser and denser. But in reality, you might have a new node added to it. Right? You will have a growing network. The sparsity of the network is sort of constant. Okay? So you can simulate this just according to this rejection sampling. Of course, you can also change this parameter. This link creation parameter, alpha d, we have in the model. Let me just go back to it. So alpha d is this, yeah. The strength, this is the retreat of Jacob to particular information source David, okay? And then this parameter alpha is controlling the strength of sequence of retreat to the link creation. If this is high, that means that if you just retreat a little bit, you're going to create to the, direct link to the information source. If this is low, you really need to retreat to a particular information many, many times in order for you to create a link. Okay? So you can change this parameter and generate data and look at this network. What is the property of this network? Right? So each time you generate network, you can do some statistics. At a particular time point, you can, for instance, if you set alpha to 0, so the creation of link doesn't depend on the information diffusion process. Right? So every time that this Jacob created a link, it's just randomly pick one to create a link. So you're getting back this traditional random graph model, this random graph model. Yeah? If you set this alpha to be something larger, okay, so you will actually create some network which is more realistic looking. You will have some small clusters connecting people. Essentially, within these clusters, people retreat each other very often. That's why they tend to connect to each other. Okay. So by writing this parameter across, you can get a diverse range of sort of network in between. Okay. Random graph and something like scale-free network. You can also look at things like degree distribution. When you have a random graph, the degree distribution, the x-axis is going to be the degree of each node, and then the y-axis is going to be something like histogram. Okay, the frequency of seeing a particular node with that kind of degree. So it's going to have essentially Poisson distribution with a particular average degree. But if you allow information diffusion to modify the link creation process, you will actually get something like a power law. Okay, so this simple generative model based on point process can actually allow you to generate some realistic looking network. Okay. So of course you can also look at the something called the diameter of the network. Essentially, you pick a two node and look at the shortest path you can get, count how many hops in this shortest path. You can look at distribution of the, you can look at the largest time, shortest path. Okay. So you also see this evolution process essentially as you generate this network. So I'm not going to talk more about this. So you will see lots of realistic kind of phenomenon or property generated by such a simple point process model. You can also look at a pattern of cascade. You will find that information tend to spread like this. Okay. Okay. So you have information source, and it's going to propagate just to nearest neighbors. Okay. It's less likely to see cascade which is very long. Okay. Like this. Actually, this is most frequent because most of the information just didn't diffuse to other people, right? So if you go to more complicated cascade, and it's just less likely to happen. Okay? You see short cascade and fat cascade instead of long cascade. You can generate this kind of realistic looking cascade, information propagation traces, just based on this model, changing the parameter. Okay, yet another example I'd like to talk about, again using this basic building block, is collaborative dynamics. In this particular case, we try to model the people patterns on a particular product, right? So what we are going to do is, for each pair of user and item, we are going to assign, for instance, a particular user David, and item 01, right, object 1, you're going to have an intensity function describing the activity, the buying activity of David to a particular product. So it's going to be a Hawkes process as well, right? So if David buy this particular product or use this particular service frequently in the recent past, the intensity is going to be high, right? Just use Hawkes process for each pair of user and product. But now you have a collection of user and product. You just use a matrix of parameters instead of, this is a single number, this is a single number. So you just look at all pair of user and product. You get this matrix of parameters. So the first matrix is going to correspond to this parameter in this Poisson process. The second collection of parameters is going to be all these parameters associated with this self-excitation term. Okay? So later on, of course, we will talk about how do we actually estimate this parameter from the data. So you have this matrix of parameters. if you don't apply some kind of regularization on these parameters, it's going to be very hard to estimate them. So this is the sort of temporal generalization of those recommendation systems in some sense. Temporal generation of collaborative filtering. Right? So in this case, you actually try to model collectively temporal dynamics of people buying a particular product. Yeah. So you can also use some of the idea for this recommendation system of collaborative filtering to tackle this problem. How am I doing with time?
We have like 10 minutes.
Okay, that's good. Yeah, and that's pretty much what I want to talk about today, right? And then I can maybe briefly talk about the question I want to talk about next, the estimation problem. But tomorrow I'm going to explain in detail. Okay. So far you have seen, this basic definition, this key quantity, which is the intensity function, and I've given you some simple example for some process which has constant intensity, and the homogeneous Poisson process, terminating point process, which you control the number of events, and the Hawkes process, where you try to capture these self-excitation effects. And then you can compose and add this intensity together, generate more complicated intensity function. Then you use it for modeling the information diffusion, use it for modeling the evolution network, and then information diffusion. And also you can use it to model the collective dynamic of a bunch of users purchase a bunch of products. Of course, all this model has a parameter in it, right? Not just one parameter, maybe a collection of parameters. Right? And of course, you fix this parameter, you can sample from these models. The question is, immersion learning is, you are providing with real data of people interacting in social network or online purchasing platform. You want to learn this parameter from the data, right? And then you don't want to just predefine this parameter. You want to learn it from data. So now that this third part I'm going to talk about tomorrow is actually how do you actually learn this parameter from data. I'm going to focus on this information diffusion model and also this collaborative dynamic model, and then how do you actually learn it. So one problem associated with this information diffusion network is sometimes the information diffusion network is hidden to you. Yeah? You don't get to see this information diffusion, the network structure. Right? What you only see is this tweeting behavior. For instance, you just see people tweeting. Okay? You don't know exactly the connectivity. Or sometimes you know the connectivity, but you don't know this exact parameter, right? How strong is this influence? You don't know the exact parameter. You want to estimate from the actual tweeting behavior. Yeah? Based on just this tweeting, essentially those time points or those cascades we have, right? Okay. So it's such a problem. Estimate the parameter in this diffusion model. So for instance, this is the idea adoption model we have seen earlier, right? So when I try to describe whether Jacob is going to adopt the idea or not, so I'm going to have a counting process for Jacob, and it's going to be a terminating point process. The intensity is going to be described by whether the parent, the two parents of Jacob, and then looking at whether Jacob has actually adopted that particular idea or not, and whether the parent has adopted the idea or not. Okay? So in this particular case, if you don't know this diffusion network, it corresponds to the scenario, you don't know whether this AJB is 0 or 1. Okay? So you don't know it. Okay, you know the network connectivity, you don't know the strengths. Okay, so you want to have a weighted graph, and then the magnitude of this value, this number here, is going to correspond to the strength of influence. So essentially, for particularly Jacob, if you want to estimate the strength of influence for all these parents, Christine, Bob, and potentially, if you don't know that whether Sophie is connected to Bob or influencing Bob or not, you also have this corresponding parameter A. JC, AJD, AJS, AJD, okay? So it's going to be a vector of parameter for Jacob. You want to estimate from data. What you see is this cascade, right? What you see is this cascade, right? Jacob is going to have a cascade. So earlier we have been talking about, the likelihood, how you actually describe a sequence of values and likelihood we are going to use it, essentially, in this parameter estimation process, okay? So I think it's about a time we can talk about how do you actually estimate parameter using convex optimization in the next lecture. Okay? Thank you very much.
We have time for questions.
does it mean that because there are millions of nodes, you worry about scalability, or you have other questions? Scale, there are several parts you might be concerned about scalability. First thing is when you simulate it, right? You need to simulate that for each node. The second thing is you need to estimate the parameter, right? And in terms of simulation, and you actually can do it for each node almost separately. Okay? So it's very scalable. We actually have some code level. It pretty much depends on the sparsity structure of the network. Okay? So we have been simulating millions of nodes. Yeah, there's no problem. Okay? And then in terms of parameter estimation, it's also very scalable. The problem is going to decompose to an estimation problem for each node separately as well. And then you can essentially, it's just embarrassing parallel to estimate parameter for each one of these nodes. We can again scale as millions of nodes. We have expanded on millions of nodes. Yeah. Yeah. Yeah, very good question. Actually, I'm trying to present a basic version. Definitely, in practice, you want to incorporate those things. So what you can do is something very simple. Yeah. So just in this edge, you can incorporate some. Each node is going to have some feature, okay, describing the interest or whatever of the particular user. And then when you're considering this edge, you're also going to take into account inner product between the feature of a pair of users. Okay. Suppose Bob is a scientist. Okay, he has some property, and then Jacob is also a scientist. Right. When you actually determine the influence between Bob and Jacob, we can look at the inner product between the features. Yeah, not just 0, 1. Okay? So you can incorporate all these things. So we call in that case topic modeling information diffusion. You can incorporate all this. So the next thing is once you learn this basic language, you can just incorporate many things. Okay, that's the wish. Yeah.
Someone asked about the scaling here getting the number of users, but I think the main aspect is the number of data you handle. And each data is a tweet or a tweet. And this is far more than each user.
Yeah.
It's the number of T.
Yeah. So you will have some learning procedure which is linear, maybe slightly super linear in the number of tweets. That's okay, right? So linear algorithm is self-scalable.
But it's okay if you learn each day, but each day there is something like a billion tweets.
Yeah, that's right. We use supercomputer to do it. Yeah, Hadoop. Hadoop, right? Yeah. So essentially, when you will find that when you try to estimate parameter for this diffusion model, you're solving some complex optimization problem. The key quantity you need to compute is gradient. The gradient, when you try to compute it, you can use multiple machines, and just each machine is computing gradient using a small set of tweets. That's how you scale it up. Right? That's why combination math, that idea, and computer science idea is good to make machine learning work in practice. Okay.
Maybe I can make a comment. If you show the losses, they are analytic. So you can actually, what you learn about the stochastic gradient, you can think that every time that you receive an event, you just compute the gradient with respect to that event.
Yeah, stochastic gradient is another thing that you can make use of, right? And actually, later on, when we asked the parameter, I have some video from Manu, which uses stochastic gradient to estimate network. You see this network change over time. That's very interesting. You're going to see